So the idea of this discussion was to try to raise transversal questions since we had very different point of views that were presented today. If there is anybody who wants to begin, otherwise I can throw a first question. There is something that was quite striking for me is that basically currently we are analyzing these deep networks as if they were as complex as a brain. We had a beautiful example with a presentation of Roger Levy, who was really doing cognitive psychology on deep networks. At the same time, they are not as difficult as a brain. We can look at how they work inside it. And I was thinking in computer vision, for example, people have been trying to understand if I take a specific neuron, what kind of pattern does that excite in the image? So I was wondering, isn't it possible to see whether there are structure which responds more to syntax, whether there are structure which responds more to semantic meaning? I know at the time when Thomas Mikolov did his work, and a number of work has been done around that, people tried to see how this space was organized in terms of semantic and so on. So I was wondering for maybe Chun Cho or Thomas Mikolov, do you know what's the state, a little bit of the art of going into the machine and really trying to understand a bit better how syntax, semantic, whatever, how is the organization done? Is it possible to do that? What stage are we at? So if any...
Mm-hmm. Thomas, do you want to say something about what you did earlier?
Yeah, sure, I can, or you can start. I also see that there may be Marco Barone actually somewhere among the speakers, so I think that he had some publications about this. So maybe I can start with the most basic things, like for example, the Retrouvez, from long time ago, we did certainly see that there's a lot of these interesting regularities that the words can be grouped together by kind of their sense, but it was really I think the beauty is in the eye of the beholder. So we did see these Retrouvez examples because we understand the language, and they are just basically copying the statistics of the training sets. And I think it's the same when it comes to these neural language models. We can certainly be trying to find out which either neurons or more groups of neurons, because it's these distributed representations, but subspaces can react to things like, I don't know, past tense or verbs in sentences and different things that are regular. And I'm sure that we will be able to find such regularities. But still, as I was trying to make the point in my talk, I think that these language models that we have at the moment are not as complex as the brains, and they are more compressing the training sets. And one can do tons of cool things with it, like the generation of the text. I certainly like it very much. I was showing these examples years before anyone else. So I certainly like these things, but I think that it's becoming kind of overrated. People assign too much meaning into these models. If you just generate a sentence that was actually pretty much present in the training set, maybe with some slight variations that you just exchange some words for synonyms, so you can't actually easily find it in the training set, but it was basically there. And it's actually not the machine that produced the sentence, it's more like the human who did actually write the sentences in the training set. So I think that it would be good to be somewhat careful and not overestimate the abilities of these models.
Okay, thanks. I don't know, Chunyun, if you have comment.
Yeah, I mean, so in terms of whether there is a syntactic, let's say, subspace or the semantic subspace within this large-scale neural network, that's been always a point of debate as well as the point of investigation. And then there have been a number of papers in recent years that show that you can recover a lot of the syntactic information by looking into the representation coming out of the BERT. And then often you don't really need too much of the labeled examples. In fact, when you try to look at the simple, let's say, Euclidean distance or the cosine distance among all those vectors, contextualized vectors out of it, you do observe that sometimes you can find some of those, the structures that correspond to syntax as well as some semantics. So I think that's fine. But also what we people have realized is that now there's a major question of, are those structures supposed to be easily recoverable from those representations that have been captured by the bird? So what people have also tried is that what if we try to forcefully remove those information, or at least make sure that those information cannot be recovered by a simple, let's say, way of probing from this model during the training time? And then will this model actually be crippled? Now, it turned out that even if we say that, okay, so linear classifier cannot, let's say, recover the syntactic structure out of it, and then we force it by using adversarial learning, and still these language models do remarkably well, for the language modeling itself as well as the downstream tasks. What that seems to imply is that there are many ways in which these large-scale models, heavily over-parameterized, can capture all those as the underlying structures, but then what is the way in which it captures it matters, and then whether that specific way has to correspond to how we understand how those underlying structures behind the language is, like it agrees with. So I think that there are a number of difficulties just coming out of having a very large model that is capable of doing a lot of things. And I believe that the Roger, can add something on top of this.
Yeah, Roger, you want to ask a question or further comment?
I actually just want to make two brief comments about that. So number one is that I think it's important to keep in mind that let's just stick with syntax and semantics. Syntactic and semantic information in human language are not fully disentangled. They are partially entangled. Right. So the kind of syntactic knowledge that is the kind of semantic knowledge that's very heavily disentangled is sort of from grammatical knowledge in humans is sort of common sense knowledge. Okay. So I can change that. So there's a wonderful ERP study about this where, if you describe peanuts as animate entities and as falling in love, you can completely change the neural response to a story about peanuts doing human-like things, and we're extraordinarily flexible that way. So we can quickly adapt to situations, and our linguistic knowledge remains relatively invariant, and our common sense knowledge that we're sort of using together, interleaving with that in very sophisticated ways, that can change. And so a major part of the enterprise actually for generalizable models is probably building models that do the right disentangling. But that disentanglement is not complete. For example, very famously, the syntactic frame that a verb can appear in is not entirely, but substantially predictable from its lexical semantics. And that's something that one would not want to eliminate, I think, from a plausible model of human-like language use. The other brief comment I'll make is that building on what Kyung-Yin was saying, that we've actually recently, so just because you can decode information from a representation, whether it's a human brain representation or an artificial neural network representation, does not mean the model or that representation is being used in the way that you might think it is based on your decoding ability. So we've actually recently done, I didn't talk about it, but we've recently started using the sort of well-known syntactic probes to try to build, you create sentences that could be interpreted in different ways that correspond to syntax, that can be represented. Those different interpretations are syntactic ambiguities. And then you can create counterfactual representations through backpropagation into the network to say, I'm going to change the internal representation so it's more like this syntactic analysis than that syntactic analysis. And then you can look downstream.
I think we have a problem of liaison. So
in the task that for and ask, when not reliably, yes, it depends on the task. And it's not, but that's that.
Okay. I think we have a problem, Roger. We didn't understand the last minute.
Oh, did I cut out?
Yeah, the last minute just.
Sorry, the very brief version of this is you can use these decoding techniques that Kyung was talking about to create counterfactual embedding representations, to try to sort of perturb the internal representation. And it turns out not always to be the case that when you do that, the downstream behavior of the model is consistent with what, like, from a human-like behavior point of view, but like we know that syntax largely mediates compositional language understanding in humans. And that would predict certain kinds of perturbations would have effects on models' downstream behavior. That doesn't always reliably come out. Sometimes it does, sometimes it doesn't.
Okay, well, thanks. Any question on the... Yes, Stan.
I think there was a very interesting challenge that was raised by Roger Levy and also by Charles, and in fact is raised by the data on the word frequency, and I would like to have your opinion on this. So Roger was showing this incredibly beautiful data, even in physics. I'm not sure if there is data where you get 6 orders of magnitude of frequency of the word, and you get this beautiful linear regularity. And that effect fits completely with a Bayesian perspective. That's what a good Bayesian would do. Is your prior should be the log of the frequency. But I don't think that's what neural networks spontaneously do. In fact, they collapse when there are very few instances when one word is less frequent by 1 million from the others. They typically collapse and don't care at all about this missing word. So what's your perspective on capturing that in neural networks? And isn't that like a blatant failure, basically, of the current approach?
Wow. So, blatant failure. Anybody wants to answer to?
So perhaps I can take this on just quickly first. Is that so what we actually observe with a very large language model is there are a number of the subtle points that we observe. So one is that when we look at the, let's say, word frequencies of the generated model, corpus, coming out of the language model that was trained on the large corpus, what we see is that depending on how we generate or decode these sentences out of the language model actually affects a lot on the final statistics. So for instance, when we build a machine translation system, we often use a greedy decoding or the beam search. There is an approximate deterministic decoding. What we see is that the generated sequences do have the kind of degeneracy you just pointed out. That is that all those rare words just do not appear at all in the generated sequences. However, when we sample from this model, like using the ancestral sampling, really just being very exact, except that with a very high variance, so we're going to sample a lot, and then trying to plot the word frequency, that frequency statistics tends to match the corpus statistics very, very closely. So what that means is that yes, there is some degeneracies coming up, but those degeneracies degeneracy needs to be kind of, let's say, analyzed in a much more fine-grained manner. So does the degeneracy arise from the deficiency of the training algorithm? Does it arise from the deficiency of how we build a network? And does the deficiency arise from let's say, our inability to use this neural net in a way that it was supposed to be used? So I think the question is actually absolutely perfect observation, and then you had a very interesting observation as well. But to answer this or to comment on this, I think that we need to specify this much more carefully and look at each of the dimensions separately.
Thanks. Yes. Yeah, you have to press on the button to speak.
Okay, maybe I can say a few words about frequency. I mean, I'm only talking about frequency in humans. In machines, I understand less. One thing is clear: if you think linguistic rules emerge out of words that children have to learn, then the words have to be there in the first place, right? So clearly, in that sense, a word has to be frequent enough in terms of token frequency to be learned. But once that's learned, the generalization process that we have studied and many others appears to be operating only on type frequencies, right? Namely counts of cardinality of sets. In fact, in some NLP-like work we found that learning to be more effective if you actually take the entire corpus and then drop the 80% of the least frequent words. I mean, so if you think about child language learning, again, you learn so much. A 3-year-old learns so much on a high frequency vocabulary range. That means that they're in effect ignoring vast majority of the words in their input. So in that sense, I think the lower frequency matters are purely a matter of noise, that children have a natural way of tuning them out because since they don't know those words. But that may be something that's useful when we try to understand generalization capacity in machines.
Thanks. Any other question? Yes, Luigi. Yes.
The task of
yes.
Interesting questions. Okay, so this is from Salvador Mascarenhas. Stefan mentioned successes of machine learning in physics. I'm curious, is there any sense in which physicists are wondering whether machine learning might offer actual theories of physics, as we do in cognitive science, or is it used purely as a tool, not intrinsically connected to the theory building?
So that's very interesting. The situation in physics is in fact very similar to linguistics. We have algorithms that can predict, for example, compute energy of a molecule in quantum chemistry, but there is no clear link with physics beyond some very general properties. For example, we know that physics has certain type of invariants, and we can see that the network implement that kind of invariance. Stability to deformation appears. But there is nothing very precise and certainly nothing related to the equations. So the equivalence of what is being wondered here in linguistics is much more related to the equations. It's how the words interact, what are the properties of the syntax, and so on. The relation between neural network experiments in physics and true physics is not more precise than what is done in linguistics currently. So I think the two problems are moving in parallel right now.
So maybe I can add just one thing. I mean, there is a paper that came out of the Flatiron Institute, the computational Center for Computational Astronomy, if I remember correctly, from the Davis Berger and Charlie Ho's group. This paper titled "Discovering Symbolic Models from Deep Learning with Inductive Biases" that was first authored by Miles Kramer, the PhD student. What they do is that they try to narrow this gap by starting with a deep neural network that was trained on a large amount of data, and then they try to distill it using a symbolic regression, so as to find a kind of a compact form that's going to explain what the deep neural net was able to predict. And then for a small, let's say, very well-controlled experiments, they were able to recover some of the interesting, let's say, more compact form of the physics behind this. So perhaps there is some hope for the promising direction that we can pursue. Yes.
That's in fact a very interesting work. You're right to point out. But what they did is they limited considerably the world in the sense that they define a physical problem with a Hamiltonian that is unknown but has to be learned. And they showed that indeed the network was able to learn the property of the underlying Hamiltonian. So the equivalent would be to work on much more controlled languages with artificial, I suppose, grammar, and then test whether we find these structures. But yes, you're right, things are moving. Yes, please.
On a different topic. I don't know if it's a question for Roger again or a follow-up on Stan, but the point I want to raise is the distinction I want to bring to the table is the distinction between competence and performance. And I think in Roger's data in particular, there was a case where more embeddings led to less of an effect. So I need to turn around to see if you're nodding. I think you're nodding. And I think it says something about the input data in particular, which mixes performance and competence by design because it's just the output of what has been produced. And there's a question as to whether we can get to what's behind performance and whether we can look at competence through the kinds of methods that Roger had exposed or by looking at neural networks just in general.
Let me just briefly comment on, you're absolutely right that you saw that in particular, so actually most of the models had some sensitivity. The strength of the pillar gap contingency was attenuated as you increased levels of embedding depth. That was a more severe attenuation for the transformer models, interestingly, which are much better performing overall in terms of perplexity, much larger training data sets. And the LSTM models were actually a little more robust. The big picture here is that I think for decades there's been an idea that so there are different positions, right? So one camp is that there's no such thing as a competence grammar, and it's all performance. And there are other camps. There are one camp that the one point of view that I've always found sort of appealing as a possible hypothesis is that, of course, that there is a competence performance distinction. And the resources and knowledge that we're using in real-time language processing are somehow that sort of performance model is sort of emergent from deep learning architectures. You know, the more classical view would probably be that recurrent architecture is sort of a priori very plausible because the fundamental idea is that there's a sort of a fixed capacity thing that you're using and everything has to be packed in that all the time because that's your brain in real time. And whatever language part of your brain does language processing. And so it's a very appealing idea. And you know, if you do see some examples that sort of look like that, but then the question is, what's the, you know, which of the sort of, a large swath of human language processing behavior is extremely well explained by a simple hypothesis, which is basically you deploy probabilistic grammar incrementally, very rapidly, according to normative rules of probabilistic inference. And you're extremely predictive, and surprisal is the linking function between most behavioral things that you can detect in real time. That covers a lot, but it doesn't cover everything. And so the question is, of the things that it doesn't cover, do you get new explanations from deep learning, for example? Or do you get new explanations from some other source? And my current view, which I didn't have time to elaborate on, is that for the large part, you don't. There are other independently motivated reasons why that attenuation occurs. You don't need to resort to sort of neural mechanisms. And then the sort of, when you look at the larger set of theory of empirical phenomena, my current, and this is something we're currently evaluating in our group, but my current take is that actually deep learning doesn't really buy you a lot of additional theoretical leverage in terms of the theory of human language comprehension. But I say that in part as a challenge because it would be very exciting if it did.
Thank you. Maybe we can take a last question or comments.
A follow-up on this. So if surprisal-based models of language processing are so general, how do they fare if you apply them to something like processing and reading music, so musical scores? Because you would expect that a lot of this could apply. And I have not followed the recent literature on this, but Roger probably has.
I mean, I'm not an expert at all, but yeah, my former student, Emily Morgan, does work in this area. Ani Patel, also, those are good people to follow. And yes, there are surprisal effects in music. There's a whole other dimension of the picture sort of too, which is like the sort of the hypothesis, like at the same time as you're like predicting, you're also making sense, right? And so there's sort of, yeah, there's a whole other class of things, which is sort of like, how does the new input sort of adjust your representation of the context? And in my view, that's actually one of the most interesting and important parts of the theory of language processing that we don't fully understand, and I'm sure that's active in music processing as well. But yes, these things do apply in music.
Okay.
Another person is David Temperley and David Huron. Those are good people to look at as well.
Well, thank you very much to all. It's now late. It was a great day, excellent talk. So I'd like to thank again all the speakers.